Okay, we're going to assume that y is a function of x in each one of these examples and go through and use implicit differentiation to differentiate each one of them. So remember, if our variable is y as we're taking the derivative, we're going to put a dy dx next to it. All right, so in this case, we're just going to use the power rule. Exponent comes down, reduce the exponent by 1, but then because that was our y, we put dy over dx, or dy dx with that. This next one is kind of a challenging one. With this, we have two things that are multiplied together. So what I'm going to do is I'm going to treat x cubed as a function f and y squared as a function g. And we're going to have to use the product rule to take the derivative. So remember, product rule says f prime times g plus f times g prime. All right, so the derivative of f, the x cubed, is going to be 3x squared. Because our variable was x, we don't have to put a dx over dx because that would be the same thing as 1. And then we copy down the g function. So multiplied by y squared is what I'm treating as our g function. Plus, this time we copy down the f function, so x cubed. Just bring that down. And we have to take the derivative of y squared. So the derivative of y squared is going to be power rule again. 2 comes down. Reduce the exponent by 1, so that's y to the first power. But next to this, we have to multiply by dy dx, because y was our variable differentiated with respect to x. One more. Derivative of natural log of y. So in this case, we know the derivative of a natural log is 1 over whatever's on the inside, so 1 over y. But next to this, we also need to include our variable there was a y, so dy dx multiplied next to it. And this does mean the same thing. If you've used different notation, this is the same thing as saying y prime instead of dy dx. But being that our notation was we're differentiating with respect to x, the d dx, that's why I used the Leibniz notation. All right, hope this helps out. Good luck.